Okay, this is a video for 7.2, day 2, repeated use of integration by parts. So yesterday's video, we learned how to do integration by parts. Today is just going to be an extension of that. What we're going to find is there are sometimes problems where doing integration by parts just one time doesn't give us an integral that we can solve. Sometimes we have to do it more than one time, and this is going to be an example of that. So in this particular problem, we have square root of 2x plus 5 under the square root. Now normally we would want to make that u, but then our du would be 2 dx. Problem is we have this extra x squared out here. Problems like this before, when we had an extra x out there, we would do a u substitution, we would solve for x, and that's still something that you can do here. But we're going to look at how to do this using integration by parts multiple times, because you will have to do it in other cases. Okay? So basically, I'm going to use my integration by parts, and I'm going to set u equal to the function that's easily differentiated. In this case, that would be the x squared. Because in this case, we have two algebraic functions, so you can't really use the I-late principle on this one, or acronym. But if I make ux squared, then du is going to be 2x dx. So again, that gets simpler. Then I'm going to take the 2x plus 5 to the 1/2 dx, and I'm going to integrate that. So v is going to be 1/2, and the reason I need that 1/2 is because, if I talk about this u substitution, if I make u the inside, I'm going to need a 2 dx. I don't have a 2 dx, so I got to multiply by 1/2. Then I got to multiply by 2/3, because I'm going to raise the power on 2x plus 5 to the 3/2. Okay, so let's see where that gets us. So we have u times v. So we're going to have 1/3 here, and then times this x squared, and this 2x plus 5 to the 3/2. So I'm going to write that down. So I have 1/3 x squared, 2x plus 5 to the 3/2, minus. Now I have to do the integral of v du. So the integral of v du is going to be this one times this one. So it's going to be 2/3. And then we're going to have the integral of x. And then we have 2x plus 5 to the 3/2 dx. Now, if there wasn't that extra x out there, we'd be all set. We could integrate this, and we'd be done. Because that was an x squared, when we did the integration by parts one time, we still have an extra x on the outside that we don't need. So I'm going to do integration by parts again. Now, in this case, u is going to be x. Du is now going to be dx. So again, this is a whole separate integration by parts here that I'm doing on this integral. dv is going to be 2x plus 5, to the 3/2. And now we got to, let's put a dx on that one. And then we're going to integrate that, which again I'm going to need a 1/2 because I don't have a 2 dx. Now I'm going to times by 2/5 and raise the power on 2x plus 5 to the 5/2 power. Okay, so I'm going to rewrite this again. So already I still have the 1/3 x squared times 2x plus 5 to the 3/2 from the original problem, minus 2/3 times, now I've integrated this integral using integration by parts, so 2/3 gets multiplied by all this. So now it's my new uv, which is 1/5 x times 2x plus 5 to the 5/2 minus v du, so that's going to be 1/5 times the integral of 2x plus 5 to the 5/2 dx. Now I have something that I can go ahead and integrate because we don't have an extra x out here. So I'm going to go ahead and do that. So I have 1/3 x squared, 2x plus 5 to the 3/2 minus. All right, this 2/5 has got, or this 2/3 has got to carry through, so I'm going to have 2/15 times 2x plus 5 to the 5/2. 2/3 is going to carry through to here, so it's going to be plus, because it's negative times a negative, 2/15. Then I've got to integrate this. I got to times by a 1/2 again because I don't have a 2 dx. Then 2/7. And then I have 2x plus 5 to the 7/2. And finally, we have our plus c. Okay. Then, of course, we have some common factors here that we're going to be able to factor out. every term has a 2x plus 5 in it, the lowest one being 2x plus 5 to the 3 halves. So I'm going to factor that out. Okay, then I look at my denominators. In this denominator, we have a 3, we have a 15. Over here, these 2's cancel out. This denominator has a 15 times 7, so that's 105. All of those denominators go into 105, so I'm going to take out 105. Okay, so what's left? All right, this term I took all that out. 105 divided by 3 is 35. So I'm going to have a 35x squared term left there. All right, 15 goes into 105 7 times. Times that 2 is 14, so I'm going to have minus 14 times the quantity 2x plus 5 to the first power, because I had 5 halves, but I took out 2x plus 5 to the 3 halves. So that's to the first. Plus, okay, we took out the 105, so all I have left on top of that is 2. And then we have 2x plus 5 squared. I took out a 1/2, leaving me with, or excuse me, I took out 3 halves, leaving me with 4 halves, which is 2. Okay, last thing to do is clean this up. If I distribute this negative 14, I have negative 28x minus 70. Okay, for those terms. Here I have 2x squared, which is 4x squared, plus, times that 2 is going to be 8x squared. And the 10x doubled is 20x, then doubled again because of 2 on the outside, so that's 40x. And then 25, because I square the 5, times by the 2 on the outside, gives me, so we'll make sure I do that correctly. So it looks like 5 squared, 25, and then times 2, so that should be 50. Okay, so I'm just going to double check everything there. Minus 28x, minus 70. Okay, plus 2, I square this is 4x squared, times by 2 is 8x squared. 10x doubled is 20x, and then times by 2 on the outside is 40x. 5 squared is 25, doubled is 50. All right, moving to the next step. We have 2x plus 5 to the 3 halves over 105. Inside I have a 35x squared and an 8x squared, so we have 43x squared. Minus 28x plus 40x, we got a plus 12x. And minus 70 plus 50, we got a minus 20 plus c. And yes, that problem is now done. Okay, so that's repeated integration. You're basically just doing integration by parts more than one time. If you do integration by parts once and you still end up with an integral that you can't solve, you got to try to do integration by parts again until you get one that you can solve. Okay, which brings up an interesting one here. This particular problem, we have an exponential and we have a trig function. Okay, so using my ILATE acronym, I am going to make the trig function, since that's a t, I'm going to make that my u. So my du would be the derivative of that, which would be 2 cosine 2x dx. I'm going to make dv e to the 3x dx. And now I got to integrate that. Now integrating e to the 3x, remember I have to have a 3 because I don't have the derivative of my power. So I need e to the u du. Since I'm missing a 3, I got to times by 1/3. So this becomes 1/3 e to the 3x. All right, so we do u times v. So we get 1/3 e to the 3x sine 2x, u times v. Sorry, I just had something pop up on the screen there. I'm not sure if it did that on the video. I had to fix my computer. Okay, so u times v minus the integral of v du. So I'm going to have 2 times 1/3, so 2/3. And then we have the integral of e to the 3x cosine 2x dx. Now some of you might be starting to see a problem here. Okay, I started out with an exponential and trig function. I did integration by parts. I still have an exponential and a trig function. And if you think about it, every time I integrate or differentiate an exponential, I'm going to get another exponential. And every time I differentiate or integrate this trig function, I'm going to get another trig function. So it's going to be this kind of endless loop of just continuing to do this. All right. I am going to continue to do this one more time. Okay. And there's going to be a reason for that. I'm going to show you what we're going to do. But what I'm going to basically do is I'm going to integrate this one more time so that I end up back where I started. Okay, that's the key thing. I want to end up back where I started. So I know this seems kind of weird, but trust me. We're just going to integrate this one more time, and then I'll show you what to do from there. I'm still going to make u the trig function now, except now it's cosine. Derivative of cosine is negative sign, and I got to multiply by 2 because of the derivative of 2x. I have dv, which is still going to be e to the 3x, so its v is 1/3 e to the 3x dx. Excuse me, this is dx, this is not. Okay, so we still have our 1/3 e to the 3x sine 2x. We have our 2/3 times. Now I did the integration by parts on this, which means I got to do u times v, so that's going to be 1/3 e to the 3x sine, sorry, it's going to be cosine 2x, u times v, minus the integral of v du. Now there's already a negative there, so I'm going to take that negative out, so it's going to be a positive 2/3. And then we're going to have e to the 3x sine 2x dx. Okay, remember we started with this. So I got to there, so I'm going to stop now integrating by parts once I get back to where I started. Okay, the next thing I'm going to do is I'm going to go ahead and distribute that 2/3. So I'm going to get minus 2/9 e to the 3x cosine 2x. I'm going to distribute that negative 2/3 to this 2/3 and get minus 4/9 integral of e to the 3x sine 2x dx. Okay, I'm going to now set that equal to what we started with, which was the integral of e to the 3x sine 2x dx. So we started with this, we integrated by parts twice, we got all this, so all of that is equal to this integral. Okay? Now, if we had an equation where we were trying to solve for x, think of this whole thing right here as being x. And over here I have that same thing. So basically on one side I have minus 4/9 times what I'm trying to solve for equals over here what I'm trying to solve for. So it'd be like if I had minus 4/9 x and over here I had x. Well, to solve that then I'd want to get these on the same side. So I'm going to take this integral right here and I'm going to add it to this integral. Okay? So I have 1/3 e, oops, left an x off of that, so e to the 3x sine 2x minus 2/9 e to the 3x cosine 2x equals, and now I'm going to take this 4/9 integral and add it to this 1 integral. So basically I have 1 integral plus 4/9 of another integral, which means I now have 13/9 of that same integral. Okay? Just like adding 4/9 x to 1x, I'd have 13/9x, except now I have 13/9 times an integral. Now remember, this is the integral we're trying to solve for. So if I take this other side of my equation, which now doesn't have any integrals in it, and multiply by the reciprocal of 13/9 over here, so I basically take this entire side and multiply it by 9/13, I now will have the solution to this integral. So I multiply that through, that's going to cancel out there. I'm going to get 3/13 e to the 3x sine 2x. In fact, I might just want to factor here. The 9 is going to cancel, so I'm going to get 2/13 e to the 3x cosine 2x. At this point, we should add a c, so plus c. And then the last thing I might do is factor out an e to the 3x/13. And so I then have 3 sine 2x minus 2 cosine 2x plus c is equal to our integral that we were trying to solve for. Okay? I went through and solved, did integration by parts twice, ended up with the same integral I started with. Take that same integral I started with then, whoops, sorry, the lights went off in my room, and add that, or I got here, so I got minus 4/9. I added that to the other side, and I multiplied by the reciprocal. And my last step was to just factor. Okay. Second part of this lesson is called integration. We're still doing integration by parts, but this is kind of a shortcut to integrating by parts. Okay? It's called the tabular method. All right? And it's when we have to do repeated integration by parts, but this gives us a shortcut way to do it. But it only works in certain cases. All right? It only works when the function that you are choosing for u can be differentiated to 0. Okay? So in this case, I have a function that has x squared, so I know if I keep differentiating x squared, eventually it'll go to 0. Okay? The other thing I do have to have is I have to have a function that I can integrate the same number of times that I differentiate this one. Okay? So actually there's two criteria to make this work. One is this function that I choose to differentiate has to be able to differentiate to 0. And then the function that I choose to integrate must integrate the same number of times. Okay? So here's how it works. I make a differentiate column, I make an integrate column, and I make a signs column. All right? In the differentiate column, I'm going to put the function that I'm going to differentiate. So I'm going to put x squared. I'm going to differentiate that until I get to 0. Okay, the function that I'm going to integrate is over here, so I'm going to put sine 5x, and I'm going to start integrating that. Now the integral of sine is negative cosine. I also have to multiply by a 1/5 because if I'm integrating sine 5x, I don't have a 5 dx to integrate it with. So I'm going to make this cosine 5x, but I have to multiply by negative 1/5. Okay, now every time I integrate this, then that means I'm going to have to multiply by 1/5. I also just have to keep track of my signs. The integral of cosine is usually positive sign, so since this is already negative, this is going to be negative 1/25 sine 5x. One more time, I'm going to have to multiply by 1/5 again, and when I integrate sine, the integral of sine is negative cosine, so since this is already negative, it's going to become a positive 1/125 cosine 5x. Okay, so I differentiate to 0, I integrate the same number of times. Now for your signs column, you're going to always start with a plus, and then from there, you're just going to alternate. So I'm going to go minus, plus, minus. Now you always want to go one more sign than you differentiated or integrated. Okay? And then here's the answer. Starting in the top left corner, you are going to go downward on a diagonal, and you are going to take the product of those three things. So we have x squared, we have negative 1/5 cosine 5x, and a positive. So that just means that you're going to basically multiply by positive 1. So that first term, then when I multiply all that together, is going to be negative 1/5 x squared cosine 5x. The same thing I would have gotten had I did a u v or u dv, and then that would have basically been u times v. Okay? I'm going to continue down the diagonal again. So I have 2x here, I have a negative half, so that's going to cancel out and just make a negative x, right? And then I'm going to have, or sorry, that's 25, not a 2. Oops. That's going to be negative 2/25x. But then that negative sign gets multiplied by a negative 1, so it basically makes that a positive. So I have positive 2/25 sine 5x is my next term. Oh, and I have an x. Forgot that. And I'm going to do the same thing on this diagonal. So I have 2, 1/25, so I'm going to have 2/125 cosine 5x. And since it's multiplied by a positive, that stays positive. And then my last thing to do is write plus c. And believe it or not, that is the same answer I would get had I done integration by parts, basically twice, and then had to integrate the last function. Okay? Might want to factor out maybe a 1/125 or something. But other than that, that's it right there. Okay? Easy as that. That's called the tabular method. All right? So let's try it again. I guess this goes down here. This is the answer to that problem. All right, so let's try it again. Here I have an x squared. So again, same thing we just did, x squared, 2x, 2 and 0. We have e to the x over 3 is our other function. We're going to integrate that. Now to integrate that, remember I would need a 1/3 dx because the derivative of my power is 1/3. So it means to integrate that, I'm going to have to multiply by 3. So it's going to be 3e to the x over 3. I go again. That means it's going to get multiplied by 3 again. So it's going to be 9e to the x over 3. Multiply by 3 again. So now it's going to be 27e to the x over 3. Plus, minus, plus, minus, plus. Okay? I go down this diagonal. So I have 3x squared e to the x over 3. I go down this diagonal. Minus 18x e to the x over 3. Down the last diagonal, I have 54 e to the x over 3. All right, don't forget plus c. And then the last thing I might do, since they all have an e to the x over 3, I'd probably factor that out. I can also take out a 3. And we have x squared minus 6x plus 18 plus c. As easy as that, that one is integrated. Okay? And again, that's called integration by parts. And I believe in your assignment, when you get to problems, I think it's like 44 to 49, somewhere like that, it'll tell you that you could do integration by parts, or the tabular method, excuse me, on those particular problems. So feel free to use that there. If it comes to a test or quiz, basically, if this method can be used, if you determine this method can be used on an integration by parts problem, then you can go ahead and use it. All right. Again, it's all going to be determined on whether or not you can pick a function that differentiates to 0, and your other function can be integrated the same number of times you differentiate the other function. If you can do that, an integration, or the tabular method for integration by parts is a useful method. Okay, and that's all I got for day 2.